Welcome, grüezi miteinander, to the Bluefield company, which is building filling machine for bottles. At this chapter of Connected System, from Thorsten Gerke and myself, Markus Meir, you will learn more about the following subject: navigation, system approach with model-based system engineering, modification in real-time field data, configuration and manufacturing, and at the end, orchestration. Innovative and practical solution, as well as equipment, needs agile innovations. Getting back immediately on a success track. The approach building filling machines for plastic bottle based on digital transformation means all processes must be driven model-based through the whole enterprise and the suppliers. Most of the informations are listed in dashboards within a web browser. They consist of tabs and widgets which are configurable and shareable with other users. Easiest way to collaborate. First of all, the navigation within a product structure, cloud-based, usable everywhere. Based on this MultiCAD structure, many simulations can be done. They are embedded in the project task, accompanied by requirements. So no further queries are needed, and the work can be done without mistake. Simulation in the platform means multi-physics up to system engineering. Our expert, Thorsten Gerke, who is keen about model-based system engineering, is interested to explain you more in this. Thorsten, the floor is yours.
Thank you, Marco, for the quick introduction. So, my name is Thorsten Gerke and I'm systems engineering expert here at Dassault Systèmes. And I'm working together with our customers on digital transformation projects in order to help them improve their overall engineering processes. In my presentation today, I would like to take you on a little journey and explain to you how to use model-based systems engineering in order to address the increasing complexity in product engineering. So the example of the bottling line is certainly a great use case to discuss model-based systems engineering because there's various disciplines involved that need to be strongly collaborating with each other. And the level of collaboration is a very important point because it decides about the level of efficiency of the overall engineering process. So historically in engineering organizations, the orgs were usually set up in different domain teams. And these domain teams evolved their own way of working, how they create data, how they manage data, and where they store all of that information. This is fine as long as you're working just within one single domain, but this becomes really a big problem as soon as you have to work across multiple different domains. And a complex product such a bottling line requires a much more integrated approach from a teaming perspective in order to finally implement that product in a very efficient way. But how can an increase of the collaboration between the different teams make the engineering process more efficient? Let's take a look at two different examples. So first of all, in order to be competitive in a market that you are serving, it's very important to be agile in terms of reacting to market changes with new product innovations. So quite often in engineering, the teams get requests for changes. So for instance, here in this case, if the customer that has ordered the bottling line is asking for a change in the requirement specification, it would mean that the teams in engineering need to sit down and get a better understanding what that finally really means. So if we were changing a requirement, the engineer needs to understand what does that mean for the subsequent engineering process. So what are the things that we will need to change in engineering now? What are the pieces in the software? What are the pieces in the hardware that need to be changed? And do we even need to make larger changes from an architectural point of view for our product? We need to get a very good understanding of that because we have to estimate from that what is the overall project cost that relates to this particular change because the customer has to pay for it. We also need to understand, do we have the resources available in order to execute that change? And last but not least, we also need to have a clear understanding, what is the risk for our project if we were doing that change? So based on that, we have to make a decision whether we do the change or not. And if we decide to go for the change, then we have to create a change proposal and finally implement that change. So the efficiency of the entire process here very much depends on the overall collaboration of the different teams. The better they collaborate with each other, the faster they can carry out the impact analysis, but also the faster and quicker they can do and implement the change. The other example relates to the fact that an engineering project always has also a governance. And governance in this case means a project management. A project management is usually either done by a project manager, or if we are talking about a very complex project, it is done by a complete project management team. And the project management team has the mission to finally craft a project plan, carry out the schedule of the different phases, but also schedule the different tasks and fill it actually with information what needs to be done. So also caring about the resource allocation. However, there needs to be a close collaboration between the project management part and also the engineering execution where we finally implement that project. So as an example, the different tasks that are defined here in the project plan, they also need to be visible in an equivalent way in the dashboard engineering environment where the engineer is finally doing the implementation. So the task also needs to come along with an input specification about what needs to be done in the task, and the engineer needs to have the possibility to attach also the output materials that he created to the particular task. So that means there needs to be a continuity between project management and engineering execution in the regard that we need to have a collaborative task management approach in between. And that kind of continuity puts us into the position that we can easily keep track of the progress of this project, but also escalate issues that maybe represent a problem for us or for our project. So in order to get the teams better collaborating with each other and to increase the overall efficiency, you finally need to break the silos around the different teams. And in order to do that, you need to establish a digital continuity between different roles in engineering. And the digital continuity would also be the foundation towards a model-based systems engineering approach. And this applies to both to the design and implementation part of the process, but also to the integration and testing part of the overall engineering process. So when we speak about model-based systems engineering, we mean with that a process where the different teams in engineering consistently create model-based specifications throughout the entire process. And that already starts with the authoring and structuring of requirements, which is the foundation and starting point to decompose subsequently a conceptual system architecture, whose output is the requirements input for the detailed engineering in software, electronics, electrical and mechanical design, where we create the component models which get subsequently tested and later on aggregated into an overall mechatronic system. And this overall mechatronic system model can then be used and tested to verify the performance against the previously defined requirements. And the overall approach that we use in the 3D Experience platform is that we put the digital twin into the center of the approach. So meaning the digital twin is the central reference for all participating stakeholders, but also for all surrounding processes. And the digital continuity in the 3D Experience platform also builds a close connection between the detailed engineering process, but also governance processes such as project management. All right, so let's see how model-based systems engineering works in action in the 3D Experience platform by the means of the modeling line example. So of course, first we start in product management, where we start to collect our requirements that we want to later implement. For that, we have created a dashboard in the 3D Experience platform, where we collect all of the intelligence data around market trends, but also data around our competitors that we use as a starting point to start our project. So for that, we have crafted a project plan that includes the definition of the different phases, but also the individual tasks that have to be done in engineering. And all of these tasks is also to create a requirements specification. So we see here the formalized requirements chapters and the formalized requirements objects that are the starting point for engineering. And these requirements are also fully traceable in the 3D Experience platform. So we see a set of requirements here that have been further refined and decomposed into more refined requirements. And all of these objects are fully traceable among each other. And the requirement specification is also the starting point then for the system architect to create the conceptual system architecture. So the system architect has created here a functional process to describe the operation of the system. And it serves as a starting point to decompose later on a logical system architecture that represents the real-world components that get later embedded into our system implementation. And the data is also connected to the 3D CAD, so there's full traceability in the entire data, across the entire data chain. So the system architecture, when it's in place, it can also be analyzed. So in this case here, we are doing a failure mode effect analysis in order to investigate the reliability of our system and to derive new requirements that can also be fed into a change management process. Afterwards, we do the complementary thing and carry out a fault tree analysis. So we analyze the system from top down to the bottom and add some additional reliability data there to figure out what's the likelihood that our system can actually fail. So now we are ready to go into the more discipline-specific engineering, and now we are going to implement here the electronic system control architecture. So that means we have designed a hardware topology for the control system and want to implement the functional process on this hardware topology. So for that, we have to define on which parts of the hardware topology the different functions will later on be allocated in order to make the system work. So now we can go into the detailed design of the electric system definition, defining, for instance, the wiring harness diagrams using 2D diagrams before we go into the detailed implementation of the 3D CAD for the electrical part. So model-based systems engineering in the 3D Experience platform also means when we are, for instance, in the detailed design, the data can come from different sources. So for instance, here for the CAD design, we have data consolidated from SolidWorks, CATIA V5 and 3D Experience in one environment in the 3D Experience platform. So now we have the implementation model of the digital twin in place, and it means we can start to do some first testing. So we have set up here a simulation model that allows us to simulate certain parts of the system. For instance, here we are running now a fluidic simulation. We can see, for instance, the fluid flowing through the different pipes. And we are analyzing now the performance of our system that we can look at, for instance, the gas pressure, because we need to know that because this is being used later on to fill the bottles. And we can also test and verify the sequence of operation of the system to see if the control algorithm is doing the right thing and keeping the sequence really as desired. And as we see here, the bottles are being filled up and they are filled with the gas. So the algorithm has been properly implemented. In the final step of the test and verification, we are going to use a real physical controller and attach that to the physical plant model. So we are doing a hardware in the loop simulation to verify our system. So this little demo here brings me now also to the end of my presentation part about model-based systems engineering, and my colleague Markus Meyer is now going to continue the journey on connected systems.
Thank you, Thorsten. I would like to continue. Navigation and remind on this 6W tags on the 3D Experience platform. The MultiCAD application made this possible, provided by the product release engineer, multidiscipline product definition, alignment and synchronization. Virtual and physical alignment, 2D schematic, 3D cabling, and Power BI. All this is possible with a standard browser, and you could navigate through the product structure. These CAD data are from different sources. Even changes could be done. In the browser widget, the structure can be changed and products can be repositioned. Think about this can be a MultiCAD assembly. This is your solution. Actually, they have to extend the emergency brake unit here at the rotary filler unit. The idea came from the service guys. They realized recurrently occurring damages at the gearbox. Their proposal: add an electromagnetic clutch to protect the gearbox. Now, all processes must be orchestrated through the various silos. Yes, collaboration is the core for all these disciplines. First, the requirement. Moreover, the project management should be step up after this. The new motor with the clutch should be a configurable variant. For sparkling beverages, an extension should be added, as well the software and electrical components must be scaled. In addition, of course, the Bluefield company is using the 3D Experience platform to drive this efficiently. This means the platform accompanies you in your end-to-end processes without silos, with a cross-access to your information wherever you are. In this chapter, we provide basic and strategic tools to drive agile innovation. The product manager has put together many information in a dashboard. Project content, competitor information, ideas with community. If needed, he shares this dashboard with others. All requirements are present and can be modified if access rights are granted. You see, there is a topic of safety and damages at the emergency stop. While producing more than 15,000 bottles per hour, the gearbox sometimes shows operations. A simulation shows the overload condition. Here, the traceability shows linkage, even between requirements and function, logical and physical products. This helped the decision for usage of a clutch. Cost intelligence shows the difference of costs with and without a clutch. Okay, the difference is feasible, so the clutch will be built in as a configurable feature further on. An already existing variant of the machine will be used to create a new configurable variant. In parallel, a project will be set up, whether from a company template or, on the other hand, by copying an existing one. Product engineering. In this chapter, we provide a fast and robust product development for best concurrent and most collaborative engineering. As mentioned before, we are working at the MultiCAD machine. The 6W tagging shows the origin in color. CATIA, SolidWorks, or others. From here or from the bill of material. A unified product structure. The filler can be opened, and in the source application, even partial. Not always the complete structure. The electric motor will be replaced by an instance with a clutch, whether from the standard library or external by one part. However, the motor together with the clutch is longer, so the length must be adapted. Therefore, some changes will be done, and the drawing will be updated. The system engineer is adding a new module to fill soft drinks containing gas. The module can be found easily with the powerful 6W filtering. With the 3D Experience platform, all entities are connected. Consolidated work on the 3D Experience platform synchronize data, save times, and prevent errors. Production planning and scheduling. In this chapter, we take a closer look to the detailed planning of work orders in the shop floor. That is the weekly or monthly capacity planning. For the typical machine lines, for the clutch, you can do this at a deeper look and see the work orders adjusted automatically. In the next panel, the overview of capacities of various machines, and in red, there are overloads of 21%. What's to do? Postpone some other work orders, and next, let us transfer some other machines. So now, the capacity is sufficient. Manufacturing, scheduling, and operation. Not only for the continuous improvement process, in the shop floor, 3D Lean can be used to brainstorm while meetings. You can flag the attendees and assign them to tasks and machines. That's very easy. You can grab ideas and flag them to machine and persons. Therefore, if the figures are not in line, you can easily grab some actions and change them. As 3D Lean works with the 3D Experience platform, there is an easy access to all the issues, geometries, and work instructions. Tentative actions created on the fly within the meeting can now transfer into formal tasks of the platform. Of course, 3D Lean can visualize the shop floor schedule plan as well as the work instruction of every workplace. That's the 3D Experience platform. 3D Experience services means predictive maintenance of mass data within the 3D Experience platform. We can analyze them and process them for easy understanding. Then the service planning can be done. For maintenance, all instruction must be prepared gradually. For better visualization, the actual part is in color. In addition, for critical operation, the mounting path can be calculated and optimized automatically. Some more added text information? Ready. At the 3D Experience platform is a web-based tool, and if you like, as well on the cloud. All information are usable everywhere and for service stuff on a mobile devices with a regular browser.